6.5 Divergence and curl. We want to go over these operators, which are called divergence and curl. They are differential operators. And we apply both the divergence and curl to vector fields. So if we have a vector field f vec, that vector field will have component functions. Let's suppose that the vector field f vec is in 3 space. Then f vec would have component functions p, q, and r. This would lead to 3 different components, so that each of these component functions is a function of a point in space, x, y, z. The divergence of the vector field is going to produce a scalar valued function. So when we look at the first component function, that component function p is providing the strength of the vector field f vec in this particular direction, which corresponds with the x direction or the I vec direction. This div is a differential operator, and so we're going to take these component functions and we're going to apply a derivative. As this p depends on more than one variable, applying a derivative, we have choices. So the choice that we're going to make for p is to differentiate in the direction it provides the strength of, namely the x direction. If we move on and we look at the component q vec, we do the same thing. We recognize that q is providing the strength of the vector field f vec in the y direction, and so that's what we differentiate q with respect to. And we have one more, r. The component function r vec is providing the strength of the vector field f vec in the z direction, and so that's what we differentiate r with respect to. As components of a vector field are scalars, these partial derivatives are scalar valued as well. And as scalar valued functions, their sum will also be scalar valued. Hence, this operator, the divergence, is taking a vector field as input and producing back a scalar valued function. Okay, very good. So we can read this as div f vec. We can read this as the divergence of the vector field f vec. And we have noted that the divergence produces a scalar. Fantastic. Let's write this down. The divergence of a vector field f vec is the same thing as the gradient operator dotted with the vector field. So if we recall, the gradient operator can be notationally represented as a vector of partial derivatives, that in the first slot we put the partial with respect to the x direction, second with respect to y, and third with respect to z. So this is nabla. then put a dot, and then the vector field fvec has component functions p, q, and r. Next, let's compute a dot product, and we know that we place this component against this component. That juxtaposition is then the idea that we take the partial of p with respect to x. P sub x. Continuing on, we want the partial of q done with respect to y. Get q sub y. And lastly, the dot product corresponding components means that we also want to add the component function r, its partial with respect to z. And then this notation is nice because the dot product is also called the scalar product, and that's helpful in reminding us that the divergence operator produces a scalar quantity. Fantastic.